morning. We have been discussing the thermal history of the universe, and I started off by telling you that we are the whole universe is filled with a microwave background radiation, and whose temperature now is around 3 Kelvin. This we see this as the cosmic microwave background radiation, and as the universe expands, the temperature of this falls as 1 by the scale factor. So, if we go into the past, when the universe was much smaller, the scale factor was much smaller, the temperature would have been just risen up inversely with the scale factor. And the whole universe is filled with such a radiation fluid, and we have been discussing the thermodynamics, the various processes that occur in a universe which is filled with such a high temperature fluid, because when you go back into the past, the scale factor gets smaller and smaller, and sufficiently back in the past, this is a very high temperature. So, we will let me now, I am going to in today's lecture I am going to essentially summarize all the things that we have learned. So, let us go back to a temperature of around 10 to the power 11 Kelvin. Okay, this is the temperature at which we start our discussion. So, when the scale factor is sufficiently small, so that the temperature is 10 to the power 11 Kelvin, at that temperature this is the temperature from which we start our discussion of the thermal history of the universe. Okay. Now, why this temperature? This temperature T is such that the temperature into the Boltzmann constant Kb, this temperature is less than the mass of the muons, but it is more than the mass into c square. Okay. It is more than the mass of the electrons. So, at this temperature of the order of 10 to the power 11 Kelvin, you do not have muons and antimuons present. You do not have baryons and antibaryons present, they have also, the mass is much higher than this. What you have is electrons and positrons. So, let me write down what you have. What you have are electrons and positrons. The temperature of this radiation, the temperature is larger than the rest mass of these particles. So, you can have pair production, you can have electrons and positrons being produced from photons, and again these two can combine to give you photons. So, this process occurs, and you have these electron positron pairs, you have photons, they are in equilibrium, and you also have neutrinos. So, there are neutrinos of 3 kinds: the electron neutrino, the mu neutrino, and the tau neutrinos. So, all of these are in thermal equilibrium. And so, you have this reaction, the electron and the positron, they can combine and give rise to neutrino and its antineutrino, and is the reverse. Okay. So, in by this process you could have either electron neutrino or mu neutrino or tau neutrinos being produced. So, all of them are in thermal equilibrium. So, this reaction is in equilibrium, and so you have all these three things, the electron positron pairs, the photons and the neutrinos in thermal equilibrium. Now, we have discussed how to calculate the energy density of this fluid, of this fluid which is in thermal equilibrium at some temperature T. We have discussed this, and let me summarize the result. The energy density, or equivalently we can write the energy density rho into c square in. So, this is the energy density. I can convert it to mass density by dividing it with c square. This can be written as n AB t to the power 4 by 2. Let me explain to you why I have written it like this. N is the number of degrees of freedom here. So, if I had just photons, we know that photons come in two different polarizations. So, for photons we have n equal to 2, and for photons the energy density is the Stefan-Boltzmann constant into t to the power 4, we know this, right. So, for photons n is equal to 2. Now, we have worked out in previous lectures the energy density when you have fermions. So, photons are bosons, and for bosons the energy density for a single degree of freedom is AB t to the power 4. We have worked this out. We have also worked out the energy density of fermions. So, for fermions, for each degree of freedom the energy density is a factor 7 by 8 times smaller. We have worked this out, and here we have electrons. The electron has two kinds of spins. We have positrons. The positron also has two kinds of spin, they are spin half particles each. So, this can have spin up, spin down, spin up, spin down along some direction. So, there is a factor of 4 over here for the electrons and positrons. These are the photons, these are the electron positron pairs, and we have the neutrinos. Now, for each kind of neutrino there is only one polarization, and there is also the antineutrino. So, the electron neutrino has one polarization, the antineutrino is another has one polarization. Similarly, we have the mu neutrino and the tau neutrino. So, the neutrinos contribute a factor of 6. So, this is the total number of degrees of freedom effectively that comes over here, and this comes out to be, so this 4 plus 6 is 10, 10 divided by 8 is 5 by 4, 35 by 4. So, this whole factor is 35 by 4, and we have to add this 2 over here. So, that becomes 35 plus 8 by 4, 43 by 4. So, at a temperature of around 10 to the power 11 Kelvin, the energy density of the universe is 43 by 4 into AB t to the power 4 divided by 2. Okay. And the baryons, they make a very negligible contribution. The dark matter, dark energy, they also make a very negligible contribution. So, this is the most dominant dynamical contribution that you have. Okay. Now, let us work out. So, we have done this, we have worked out all the relevant required formulas for this earlier. So, this is the state of the universe at a temperature of around the energy density at a temperature of around 10 to the power 11 Kelvin, and the dynamics is governed by this. Let us work out the the expansion of the universe at that epoch. So, we know we have dealt with the equations governing the expansion in quite some detail. And we know that it is governed by this equation A dot by A square, that is the Hubble parameter square, is equal to 8/3 pi g rho. Okay, we have worked this out, you can, and this here, the density here is all in this relativistic fluid at a temperature of around 10 to the power 11 Kelvin. So, this is 8/3 pi g, then I have n a b t to the power 4 by c square. So, this is the equation governing the expansion of the universe. And we have also seen from the first law of thermodynamics that when a relativistic fluid expands, the temperature into a to the power 4 T into A is a constant, or we have we have seen this in from even from the both the Fermi-Dirac and the Bose-Einstein distribution, that as the universe expands. We have also seen it in terms of the energy density, that for a relativistic fluid rho a to the power 4 is a constant, which means that T into A is a constant, because rho is proportional to T to the power 4. Okay. So, this we can write, this constant we can write as, let us say, some T naught into some A naught. Here naught does not refer to present, it is some fixed value. So, as the universe expands, the temperature falls as 1 by A, that is the basic thing which I told you right at the beginning. So, this equation now can be written as A dot by A square is equal to some constant. So, we can write T is equal to T naught A naught by A, and putting this in here, we can write this equation as some constant k by A to the power 4. So, this constant over here k is this factor is this factor over here, right. So, we can write this equation like this, and we can integrate this now. What we have to do, this is a radiation dominated universe. So, the way to integrate this is to write it as dA by dt. So, this now becomes dA by dt. I can take square root, I can bring this A to the power 4 over here, which cancels out with A square. So, I have a square in the numerator over here, and now I take square root of the whole thing. So, what I have is this is equal to k, or d a square is equal to 2 k t dt, sorry, I can get rid of this here, and there is a constant of integration plus C1. And so, this gives us the fact that A is equal to, rather I can write it the other way around, T is equal to, so I want to write the time T is equal to C1 by 2k, and I have a square some constant, this is a constant. And then putting in the value of k, so we put in the value of k, which is a constant, and the fact that the scale factor A is T naught by T naught A naught by T, what we get is that this is equal to, the time is equal to, let me just put back all the values, this will be square root of, this should be the square root of k. This should also be the square root of k. Okay. So, T is equal to I can write it like this. T is equal to these factors over here plus C. Now, how much is the square root of k? Let me just write it here. So, what we need is 1 by the square root of k, 1 by the square root of k is equal to square root of 3 by 8 pi g n a b and then I have 1 by T naught square A naught square, that is the square root of 1 by square root of k, these factors here, right. So, when I plug this in here, this term over here cancels out exactly with this, and this 2 can be taken inside. So, what we have finally is that T is equal to square root of 3 by 32 pi g n a b, the Stephen-Boltzmann constant, 1 by t square plus a constant. Or there should be a factor of c also, some speed of sorry, we missed that out, there is a c square here, So, there should be a factor of c square here. So, this should be in the denominator c square. Okay. So, please just check this coefficient. The main point is that there is a 1 by t square over here. Okay. Now, we have already calculated what this n is. We know the Stephen-Boltzmann constant, the Newton's gravitational constant, all these constants are known, and for the particular fluid that we are talking about, which has the electrons, positrons, the photons and the neutrinos, this n is 43 by 4. So, putting in those values, what you get is that the time is T by 10 to the power 11 Kelvin to the power minus 2 plus some constant, and the factor outside is 0.994 seconds. Okay, if you just put in these values 43 by 4 and the value of g and the Stephen-Boltzmann constant, etc. So, this sets the expansion, this tells you the expansion time scale of the universe at the epoch when the universe the temperature of the universe was around 10 to the power 11 Kelvin. Okay. Just to get a feel for these numbers, let us ask the question, how much time does the universe take to expand so that the temperature falls from 10 to the power 11 to 10 to the power 10 Kelvin. Or rather, let me ask the question, how long does it take to fall? This formula will not be valid over here. How long does it take for the temperature to fall from 10 to the power 10, 12 to 10 to the power 11 Kelvin? So, the question is, how long does it take the universe to expand so that the temperature falls from 10 to the power 12 Kelvin to 10 to the power 11 Kelvin? Okay. So, when you put 10 to the power 12 over here, this gives you 10. So, 10 to the power minus 2 is 100. Okay. So, it is 1/100th of this number plus a constant. So, this corresponds to T is equal to 0.994 by 100 square 100 plus C, and this corresponds to 0.994 plus C. So, you have to just subtract these two. It turns out that the time delta t which elapses between when the universe is 10 to the power 12 Kelvin and 10 to the power 11 Kelvin, this time is around 0.98 second. So, it is a fraction of a second. The universe cools from 10 to the power 12 Kelvin to 10 to the power 11 Kelvin in a fraction of just a second. In 1 second it has cooled here. Okay. And the cooling previous to this is going to be much less than a second. That is obvious from here, right. The larger the temperature becomes, the faster it cools. Okay. So, we have a feel for the numbers regarding the cooling rate over here. Now, let us move on. So, what happens now is that as the temperature of the universe falls, as the universe expands, the temperature falls, and when it hits a temperature of around 10 to the power 10 Kelvin. So, when it hits over here somewhere, so it falls below 10 to the power 11 and it hits somewhere around 10 to the power 10 Kelvin. What happens is that the reaction rate, this is a weak interaction. Okay. This is through the weak interaction. Now, there are two things going on simultaneously. One is this reaction taking place, electron positron, they combine, give rise to neutrinos. Neutrinos can again and anti-neutrino can combine to give rise to electron positron. Okay, there is a reaction rate for this. This is through the weak interaction. The other thing is that the universe is expanding. Now, and the expansion of the universe will just try to freeze the particles as they are. Okay. So, one has to now look at the ratio of the reaction rate and the expansion rate. Expansion rate is 1 by the Hubble parameter, we know this, right, that is the expansion rate of the universe. And this ratio falls less than 1 falls below 1 at around 10 to the power 10, slightly above 10 to the power 10 Kelvin. And once this ratio falls below 1, the neutrinos have essentially decoupled. They no longer are in thermal equilibrium, and you can treat them effectively as free particles. And we have discussed what happens to the distribution function for free particles. It remains frozen. The distribution function does not change. The momentum of the particle just scales as 1 by a. Right, this is something that we have discussed. So, once the neutrinos decouple, and their distribution function remains frozen, because the particles do not interact with anything after this. Okay. And 10 to the power 10 is also the scale, the energy scale. 10 to the power 10 Kelvin is also the energy scale where the electron positrons recombine, the mass scale of the electron positrons. So, slightly after this, so this occurs first, the neutrinos decouple first, and after this the electrons and positrons, so the neutrinos have decoupled, they are just now freely expanding, freely moving particles in an expanding universe. The distribution function does not change, and as the universe expands, their distribution function remains fixed. And slightly after this, what happens is that the electron positron annihilate. The electron positrons annihilate. Now, the electrons and positrons are charged particles, and they are in thermal equilibrium with the photons. So, you have now got two things. You have the neutrinos which have decoupled. The electrons and positrons are still there for some time, and then the temperature falls below the mass scale of the electron positron pairs. So, they annihilate, and the extra energy that is there in the electron positrons pairs, that gets converted into the photon energy. We have discussed, we have worked out the how the relation. So, what happens is that this extra energy gets pumped into the photon energy. So, until this electron positron annihilation, the temperature of the neutrinos and the temperature of the photons, even though the neutrinos were decoupled, it still remains the same. Okay. But the moment the electron positrons annihilate, the energy in these pairs of particles gets dumped into the photon. So, they gain more energy, and the energy of the photons rise relative to the energy of the neutrinos as a consequence of this. Now, this whole thing is an adiabatic process, and the entropy is conserved through this whole process, and we have worked out this, the implications of this in the last in previous lectures. So, you have to balance the entropy before the reaction, before this annihilation. So, before the annihilation, you have the entropy in the photons, you have the entropy in the electrons and the positrons. the temperature of all of these is the same as the temperature of the neutrino. After the annihilation, all of this entropy goes into the entropy of the photons alone. So, you can now from this balance of entropy you can determine the temperature, the ratio of the temperature of the photons after this annihilation to the temperature of the neutrinos. The neutrinos have just expanded. Okay. So, we have worked out this this in some detail in an earlier lecture, and I showed you that the temperature of the neutrinos, as a consequence of this, the temperature of the neutrinos falls below the temperature of the photon fluid, and the temperature of the neutrinos is a factor of 11 by 4 4 by 11 to the power of 1/3 the temperature of the photons, and the photon temperature, if you take this to have a value of 2.725 Kelvin, okay, then the temperature of the neutrino comes out to be 1.945 Kelvin. Okay. So, what so the neutrinos have a slightly smaller temperature. The energy density in the neutrinos is also smaller, not only because the temperature is smaller, but because the energy density in fermions is 7/8 that in boson. So, there are these two factors which go in, and you can also work out the energy density. We have worked it out, and the total relativistic, we believe there is evidence which tells us that the neutrinos are most probably massless, not massless, but they have extremely small masses, and the masses are smaller than the temperature now. So, you can treat them as relativistic particles. Most that's there is indication that you can treat them as relativistic particles, and you have three species of neutrinos. You have this photons. So, the total relativistic mass content in the universe after once the electron positrons have annihilated is there in the combination of these two. So, you have the photons at this temperature, no, not at this temperature, with the ratio of these given by this. Okay. Presently, they have these temperatures, but in the past the temperatures would have been different, and you also have the neutrinos. There is a temperature difference between them. There could be, we have taken that there are three flavors of neutrinos. Okay. The neutrinos are decoupled from the photons, but as the universe expands, the energy density falls as the temperature falls as the scale factor. Okay. So, after the annihilation, the temperature of the CMBR goes up relative to the temperature of the neutrinos, and one can again go back to this and calculate the expansion, the expansion of the universe, right. So, now you have two relativistic components. So, the value of n is going to be different, and the temperature of these two components also is different. So, one has to rework this. You now have photons and neutrinos only. The temperatures are also different, but you can work out, one can put in all those numbers, but both of them scale with the expansion in exactly the same way. So, you can put them all together, those differences will only be in the factor over here. They all scale as t to the power 4. So, those differences will occur over here, and finally, when you do it, you will again get, when you integrate the equation, you will again land up with exactly something exactly like this, something exactly like this, just that the number over here is going to be different, that is all, and the constant is going to be different. So, what you get when you do it, when you do this, is T is equal to, again you can write it in this way, T by, now you can write it in terms of 10 to the power 10 Kelvin minus 2, and what you have is 1.78 second plus a constant. Okay, so this is the expansion of the universe after the electron positron pairs have completely annihilated, and this temperature refers to the temperature of the CMBR. The temperature of the neutrinos is obviously smaller than this. Okay. So, let us again make an estimate of the time scale involved. So, let us see how much time it takes for the universe to cool from 10 to the power 10 Kelvin to 10 to the power 6 Kelvin. So, when you are going to compare these two, the time it takes from here to here, 10 to the power 10 in this is going to give you a factor of 1 over here, 10 to the power 6 in this is going to give you a factor of, so we have 10 to the power 6 and 10 to the power 4. So, the difference 10, 10, so they have 10 to the power 4 and 10 to the power 4 square, 10 to the power minus 4 basically, and 10 to the power minus 4 minus 2, 10 to the power 8. So, this we can actually forget about this term. So, what we find is that it takes around 5 years, you put in the value for the universe to cool from here to here. Okay. So, the expansion rate, the time scales get larger, the expansion rate gets lower. Okay, the time scales get larger as you reach to lower and lower temperatures. The point of this exercise, which of these formulas, is that you can directly relate the temperature of the universe to the time. Okay, it sets a time scale also. The temperature of the universe also sets a time scale. Okay, and the time scale gets larger and larger as the temperature gets cooler and cooler. Now, once you hit temperatures of around 10 to the power 6 Kelvin, you have to take into account not only the relativistic components. In this analysis, we have included only the relativistic components, that is the CMBR and the neutrinos. But once you hit temperatures of around 10 to the power 6 Kelvin, the dark matter, the dark energy, dark matter essentially, dark energy becomes dominant only much later. The dark matter also starts making a contribution to the dynamics. Okay. So, once you hit a temperature of around here, the dark matter also starts coming into the picture, and then you have the epoch of matter radiation equality, where the density. So, here at high temperatures in the past, the universe is, the energy density, the mass density is dominated by the radiation. As the temperature falls, the energy density in the radiation also falls. and at a temperature of around 10 to the power 6 Kelvin, you start getting effects. And lower temperatures lower than this, you have to start including the effects of the dark matter, the other other components of the universe. Okay. So, I have very briefly gone through the thermal history of the universe, and there were mainly two processes. One was the neutrinos decoupling, and the other was the annihilation of the electrons and positrons. The net consequence of this is that we are left with a background of neutrinos which have a temperature slightly less than the temperature of the CMBR. Now, it is unlikely, the neutrinos are weakly interacting particles, and it is unlikely that in the near future at least we shall be able to detect the neutrino background, right, because they are very weakly interacting particles, and you would require, when you put a detector to detect these neutrinos, but the temperature, the number density of these neutrinos is so small, the fluxes would be so small that it would be not possible with the present technology to detect this neutrino background, but it is there. Just like you have the photon background. The photon background, presently there are around 400 photons per centimeter cube. The neutrino background is somewhat less, few hundred per each species neutrinos. Now, there are certain assumptions. So, okay, this is the main outcome of this. So, we start off with a situation where all of these are in equilibrium, then slowly the neutrinos go out of equilibrium, the positron electrons annihilate, and finally you are left with the photons. The neutrinos have decoupled. This picture we have to keep in mind, it is going to be very important for the future discussion. Okay, so this is the crucial the thing, the point that one has to bear in mind in the future, in our future discussion. Okay, and there are a few assumptions which we have made in this discussion. So, let me just briefly remind you what they were. One assumption was that the neutrinos have assumed to be relativistic. That is, the masses of the neutrinos have been neglected. Now, this picture that we have discussed would be modified, would get modified under certain circumstances. Let me tell you what these circumstances are. Now, at 10 to the power 11 Kelvin, the neutrinos are in thermal equilibrium with photons and electron positron. This whole thing is in equilibrium. Now, if the neutrino had mass, if the neutrinos had a mass, and if that mass were more than 10 to the power 11 Kelvin, if the neutrinos had a mass which is more than 10 to the power 11 Kelvin, some enormous mass, let us say 10 to the power 12, 13, somewhere over there, then what would happen? Then what would happen is that by the time the universe has cooled to 10 to the power 11 Kelvin, the neutrinos would still be in thermal equilibrium with this fluid, but the temperature would be less than the neutrino mass. So, if the temperature is less than the neutrino mass, the neutrino antineutrinos would annihilate, because they are in equilibrium, and the neutrino number density then would be tremendously suppressed, just like the electron positrons annihilate when the temperature falls below the mass of the electrons and positrons. Similarly, if the neutrinos had mass which were larger than 10 to the power 11, so if the neutrinos went massive when they were in equilibrium, then the neutrinos and antineutrinos would annihilate, and the species which had mass, the abundance of that the number density of that species would be drastically reduced relative to the number densities of the other species. Okay. If this So, if this suppose the mass were less than 10 to the power 11, say the mass were 10 to the power 8, if the mass were such that it corresponds to 10 to the power 8 Kelvin, then what would happen is that the neutrinos would be out of equilibrium by the time the temperature falls below the mass. Once the neutrinos become out of equilibrium, there is no way that they can annihilate. So, even though they were massive, they would still, the distribution function would still be that of relativistic particles. Okay. So, this is one consequence, one possible deviation from the scenario that we have discussed. Now, the neutrino mass is severely constrained. There are several constraints on the neutrino mass, and there are a variety of constraints. I can briefly mention some of them. So, there are constraints if the neutrinos, so suppose the neutrinos had a mass which is less than, so had a mass so that it is less than 10 to the power 11 Kelvin. So, when they were in equilibrium, they were relativistic. The mass, let us say the mass is some 10 to the power 5 Kelvin, something corresponding to that, or even less. Okay. Then what would happen is they would be relativistic when they went out of equilibrium, and once they go out of equilibrium, the distribution function remains fixed. We know that the present number density is some few hundred, 110, something like that, neutrinos per centimeter cube. So, if they had a mass, we can exactly predict what the mass density of these neutrinos would be, and if the mass density that you predict turns out to be more than the critical density of the universe, then the universe, it may turn out that the universe should have collapsed by now, which is obviously absurd. So, that this requirement puts restrictions on the neutrino mass. The neutrinos, even if they have a mass, the mass cannot be so high that the density crosses the critical density or something like that. Okay. So, this puts limits on the neutrino mass. Now, there are more stringent limits from observations of anisotropies in the cosmic microwave background radiation and from the large scale distribution of galaxies. So, the large scale distribution of galaxies, the large scale structures in the universe and the cosmic microwave background radiation, these put quite stringent limits on the neutrino mass, and the masses are expected to be less than fraction of electron volt. I shall give you the exact numbers in later lectures. There are constraints on the neutrino mass. There are indications that the neutrinos do not have zero mass, they do have some mass. These indications come from solar neutrino observations, but they do not tell you what the neutrino mass is, they tell you the mass difference between different kinds of neutrinos. And these mass differences are predicted to be, they are predicted to be non-zero, but extremely small. Okay. There are experiments, there are some other experiments from neutrino from the double beta decay, and there are certain experiments now which seem to be indicating that the neutrinos, the mass could be, the mass of all the neutrinos combined could be quite large, but again this, so I shall give you, so let me just, so the main point I am trying to make here is that the neutrino mass is constrained. I shall be giving you the exact figures in a later lecture, but the scenario that we have considered would be modified to some extent if the neutrino mass were extremely large, so that they became non-relativistic when they were in thermal equilibrium. But there are direct, now there are direct, there are measurements of the neutrino mass difference, and there are restrictions on the neutrino mass which seem to rule out those scenarios, and I shall give you the detailed figures in a later lecture. The other possibility that again would bring about variations in this scenario is the fact